This podcast was created as a supplemental learning resource for this course. The content is based on assigned course materials, including open educational resources, textbook chapters, instructor-developed explanations, examples, and applications connected to course topics. AI tools were used to help transform course material into a conversational podcast format, including the use of AI-generated narration. The AI narration is intended to make the material more engaging, accessible, and flexible for students. However, the podcast should not replace careful reading of assigned materials, reviewing course lectures, or completing course activities. Any interpretations, examples, or explanations included in the podcast are provided for educational purposes and are the responsibility of the instructor. Students should rely on the assigned readings, course lectures, and official course materials as the primary sources for exams, assignments, and class discussions.
Usually when you talk about like a medical diagnosis, there's this distinct expectation of precision. It feels almost like engineering, you know?
Right, yeah, like it's a completely mechanical problem.
Exactly. You fall off your bike, your arm hurts, you go to the hospital, they put you in front of an x-ray machine, take the image, and the doctor just points to this jagged white line on a glowing screen and says, well, there it is, that's the break.
Yeah, and it is deeply comforting to the human mind to have that level of visible categorization. I mean, we are desperate for certainty.
Oh, absolutely.
When a problem is physical and mechanical, our tools let us pierce right through the ambiguity. We just see the definitive truth of the matter.
Right. It's a binary reality, broken or not broken. The evidence is visible, tangible, and clean. But then
you step into the behavioral sciences.
Yeah, exactly. You step into the world of neurodevelopment, trauma, psychology, and suddenly that x-ray machine is entirely useless. You are looking at a diagnostic landscape that is, well, incredibly murky.
It's the absolute definition of diagnostic muddy waters.
Right, because you're trying to measure concepts like happiness, cognitive load, anxiety, or, memory retention. There is no glowing white line on a screen for a broken memory.
No, there isn't. The phenomena we care about most deeply in the behavioral sciences are invisible constructs. I mean, you can't put a ruler next to a feeling of existential dread.
Wow. Yeah, that's a great way to put it. You can't measure dread with a tape measure.
Exactly. So we have to rely on proxies. We rely on surveys, behavioral tasks, reaction times, physiological markers. We gather data, but that data is inherently noisy, it's messy, and it's indirect.
And that profound murkiness is exactly why we are here today. Welcome to the Deep Dive. We have a very specific mission tailored just for you as you navigate the complexities of your behavioral sciences statistics course.
Yeah, you've had a pretty pivotal moment in your studies right now.
You really have. Chapter 5, titled Foundations for Inference. And our goal today isn't to just read a syllabus back to you. Our mission is to pull back the curtain on how researchers actually uncover the truth when they are swimming in those muddy waters we just talked about.
Right. We want to explore the philosophical architecture of how we know what we know.
Because up until this point in your statistical journey, you've basically been living in the world of descriptive statistics.
Yeah, you've been summarizing data, drawing those beautiful graphs, calculating means, medians, standard deviations, all of that.
Right. But describing the data only tells you what happened in your specific isolated sample. It does not tell you why it happened.
No, and it certainly doesn't tell you if that finding means anything for the larger human population, which is, usually the whole point.
Exactly. This is the moment we cross the threshold into inferential statistics.
Which sounds like a really intimidating leap.
It does. Inferential statistics feels like heavy academic jargon. But if we strip away the intimidating terminology, it's essentially the ultimate detective tool for the behavioral sciences.
Yeah, I like to think of it as a system of logic. Consider inference as the rigorous toolkit that allows us to reason from our messy, limited, imperfect data to make, broader, confident claims about the real world.
And crucially, it's a system that explicitly accounts for the unavoidable uncertainty that comes with measuring human behavior.
Right. We don't pretend the uncertainty doesn't exist. We build a mathematical framework to understand exactly how much uncertainty is in the room with us.
So just a quick note on how we're going to approach this together today. We are your learning companions on this journey. We're going to focus intensely on the conceptual logic.
We want you to understand the why and the how behind these ideas before you ever sit down and try to memorize a single formula.
Because if you try to memorize equations without understanding the philosophy of inference,
it's like trying to memorize the dictionary without knowing how to speak the language.
Exactly. It's pointless. But once you understand the underlying concepts and the elegant logic of how chance operates, the formulas you encounter later will simply look like shorthand.
Yeah, they'll just be a faster way to tell a story you already deeply know how to tell.
So let's start with the big picture and interrogate why we even need inference in the first place.
Okay, let's do it.
To do this, let's explore a highly relatable, arguably vital scientific inquiry. Does watching cat videos on YouTube actually increase human happiness?
Ah, a question for our age.
Right. It sounds frivolous, but the mechanics of how we would prove this are the exact same mechanics we use to test life-saving clinical therapies.
They absolutely are. It's the same architecture.
So let's walk through a basic experiment using this feline premise. If we took a flawed approach, we might just find 100 people, ask them how many hours of cat videos they watch a week, and then ask them to rate their general happiness.
Right, just a simple survey.
Yeah. And if we find a positive correlation, meaning the people who watch more videos also report being happier, we might be tempted to claim victory right there.
But from previous lessons in methodology, we know that correlation entirely fails to establish causation. It's the classic trap.
Right, because maybe watching the cat videos actively injects joy into their lives.
or, equally plausible, maybe being a naturally happy person makes you more prone to seeking out playful content online in the first place.
Exactly. Or the most dangerous possibility, a hidden third variable, like perhaps having a vast amount of unstructured free time and disposable income causes you to both be generally happier and have the luxury of watching endless cat videos.
Yeah, the observation alone tells us nothing about the direction of the effect.
So to isolate the actual cause, we have to intervene in reality. We need a controlled experiment.
We need a manipulation and a measurement.
Right. In our scenario, the independent variable is the strict amount of time a participant is forced to spend watching cat videos.
Okay, so we recruit 50 subjects.
Yes, 50 subjects. We randomly assign 25 of them to sit in a room and watch exactly 1 hour of cat videos. And we take the other 25 and randomly assign them to watch exactly 2 hours.
Now, I want to focus on the phrase random assignment for a moment because it is the bedrock of the entire enterprise.
It really is.
By randomly assigning participants, we are utilizing the brute force of probability to try and equalize the two groups before the experiment even begins.
Right. We're trying to ensure that the naturally happy people, the caffeine-deprived people, the cat haters, are somewhat evenly distributed between the 1 hour room and the 2 hour room.
Exactly. So once they finish their mandated viewing, we introduce the measurement, which is the dependent variable.
We give everyone a psychological assessment that scores their current happiness on a highly precise scale from 1 to 100.
So now we have the two critical components, the independent variable of time and the dependent variable of happiness.
We gather all 50 scores, we separate them by group, and we calculate the average happiness score for the 1 hour group and the average happiness score for the 2 hour group.
And this is where the narrative usually gets dangerous.
Oh, very dangerous. Let's imagine the data comes back. The average happiness score for the 2 hour group is, in fact, higher than the 1 hour group.
The immediate, overwhelming human impulse is to point at those two divergent numbers, call a press conference, and yell, "Look at the data. 2 hours is definitively better than 1. Cat videos cure sadness."
I would absolutely write that headline. I mean, it feels intuitive, right? You changed a variable, you got a different result, therefore your change caused the result.
Right.
But here is the core problem, and the entire reason inference exists. How do we know with absolute scientific certainty that the happiness scores changed because of the viewing conditions?
The unsettling truth of behavioral science is that even if your experimental manipulation did absolutely nothing even if watching cat videos had zero impact on human emotion whatsoever, you would almost certainly still see a difference between the averages of those two groups.
Wait, I need to push back on that. If the videos have literally zero psychological effect, shouldn't the two groups report the exact same average happiness score? Why would one group score higher if the intervention is useless?
Because of the profound chaos of human variance. I mean, you are not measuring the output of identical calibrated machines. You are measuring human beings.
Right, that makes sense.
Every single person in that study brings a different baseline level of happiness into the room. Some people are naturally effervescent. Some people are clinically depressed.
Some people just found $20 on the sidewalk, and others just received a stressful text message from their boss.
Exactly. So think about this for a moment. Why is uncertainty completely unavoidable? Why can't we just design a perfect experiment that eliminates it?
Because any measurement you take in the behavioral sciences inherently contains natural variance. You can never control everything.
No, you can't. When you randomly divide 50 unique, complex humans into two groups of 25, just by the sheer luck of the draw, one group is probably going to end up with slightly more naturally cheerful people than the other.
So even before you hit play on the first video, before the experiment has technically even begun, one group's average happiness is already destined to be slightly different from the others.
Precisely. And that natural, unavoidable variation is what we refer to as sampling error or sampling variability.
It dictates that whenever you take a sample of complex data, the resulting metrics are going to bounce around a bit randomly.
Going back to your opening X-ray analogy, finding a statistical difference between the two groups in our data is a lot like finding a suspect standing over a body at a crime scene.
Right.
Just because they are physically present, standing there with the evidence, does not mean they actually committed the crime.
Yeah, in the realm of statistics, chance, this natural sampling error we keep talking about, is the ultimate repeat offender. It's a suspect at every single crime scene.
It is always lurking in the background, perfectly capable of producing differences between groups that look incredibly meaningful, but are actually just random, meaningless noise.
And what this means for you as a researcher is that statistical inference is the rigorous, uncompromising process of interrogating that specific suspect.
Yes, it is the mathematical framework we use to figure out if chance is a likely or an unlikely culprit for the difference we are observing in our data.
Because if we can build a strong enough case to prove that chance is a highly unlikely explanation for our findings, then we finally earn the right to point the finger at our actual manipulation.
The cat videos.
Exactly, the cat videos. But we cannot ethically make that claim until we thoroughly investigate exactly what chance is capable of doing.
And to interrogate chance, we have to understand its origins. We need to understand where numbers come from before we measure them, which introduces this somewhat abstract but entirely essential concept of a distribution.
Yeah, I have always conceptualized a distribution as like the universe's backstage area. It's the hidden machinery operating behind the scenes of reality.
That is a highly accurate mental model. A distribution acts as a set of hidden constraints. You can picture it as a massive, complex, number-generating machine.
Right.
The specific settings of that distribution determine which numbers are highly likely to get spit out into the observable world, and which numbers are exceedingly rare or even impossible.
To ground this abstract idea, imagine the simplest machine possible, the uniform distribution. Picture a flat horizontal line on a two-dimensional graph.
Okay, I'm picturing it.
The x-axis running along the bottom contains the numbers 1 through 10. The y-axis running vertically represents probability, scaling from 0 to 1. Our horizontal line cuts straight across the graph at exactly 0.1 or 10%.
And the rules of this specific machine are perfectly egalitarian. If this uniform distribution is spitting out numbers, every single integer from 1 to 10 has the exact same equal probability of emerging.
It's a perfectly fair system. There's a 10% chance it produces a 1, a 10% chance it produces a 2, and so on, all the way to 10.
The theoretical math is pristine. If I walk up to this perfectly fair distribution machine and press the button exactly 100 times, generating a sample of 100 numbers, the theoretical expectation is clear.
I should receive exactly 10 ones, exactly 10 twos, exactly 10 threes, straight across the board.
Right. That is the expectation based on infinite probability. But consider what actually happens when you draw a finite sample from this machine.
That's never perfect.
No, it almost never is. If you take those 100 randomly generated numbers and chart their frequency on a histogram, a bar graph showing how many times each number appeared, the result is visually jarring.
Yeah, because if the sample perfectly mirrored the distribution, every single bar on that histogram would be the exact same height. It would hit exactly the number 10 on the axis, creating a perfectly flat top.
But the reality of a sampled histogram is wildly different. It's bumpy, it's jagged, it's chaotic.
You might find that the number 4 occurred 13 times, while the number 7 only occurred 6 times.
And the jaggedness of that graph is a visual representation of sampling error. It is a massive conceptual realization.
Oh, absolutely. Even when you have godlike knowledge of exactly where the numbers originated, a perfectly flat, utterly fair distribution, the actual finite sample you pull from it is intrinsically messy.
The analogy of the grocery store is incredibly potent here.
Huh.
Picture a massive supermarket that is offering free samples of a new artisan cheese on toothpicks.
Okay, I love cheese.
If you were somehow capable of gathering up every single piece of that specific cheese in the entire store, the inventory in the back, the displays in the front, you would possess the entire population of that cheese.
You would have perfect, complete knowledge of exactly how much cheese exists and what its total reality looks like.
Right. But the reality of science is that researchers are essentially the customers. We are never allowed to take the entire population.
No, we don't have the time, the budget, or the physical capability to measure the baseline happiness of every single human being currently alive on planet Earth.
We are forced to just take a small handful of cheese samples on toothpicks and walk out of the store. We rely entirely on a limited sample.
And this is where we must sound a massive alarm for a common cognitive trap. There is a deep, almost instinctual psychological flaw, where humans assume that a sample statistic is a perfect, miniature mirror of the population parameter.
Yes, we desperately want to believe that if we take a sample of 50 people, those 50 people are a flawless, pristine microcosm of the entire human race.
We want the sample to be a perfect hologram of the whole. But that bumpy, jagged histogram from our uniform distribution machine mathematically shatters that illusion.
Individual samples are noisy, messy, imperfect, and sometimes downright deceitful representations of the populations they originate from. They are incredibly fuzzy around the edges.
Right. Imagine returning to our fair, uniform machine and drawing 10 separate samples, each containing 20 numbers. If you graph all 10 of those small samples as individual histograms side by side, the results are chaotic.
Not a single one of those 10 graphs will look flat. One graph might have a massive spike on the number 3, making it look like the machine favors 3s.
Another graph might have a deep valley on the number 8, suggesting 8s are rare.
And if a researcher was handed just one of those bumpy histograms without knowing where it came from, they would confidently conclude they had discovered a complex, non-uniform pattern.
But we possess the omniscient knowledge that the machine is perfectly uniform. The bumpiness, the spikes, the valleys, they are pure illusion.
They're phantoms created entirely by chance. It is sampling error actively at work, disguising random noise to look like a meaningful, structured pattern.
So if finite samples are inherently this noisy, chaotic, and fundamentally misleading, it poses an existential threat to research. How can any scientist ever hope to learn anything objectively true?
Right. How do we ever pierce through the noise to see the actual shape of the true distribution hiding behind it?
The antidote to chance is sheer volume. We bring in a weapon to flatten the noise. In statistical notation, that weapon is the letter N.
Capital N stands for your sample size. It is the total number of individual observations or participants in your sample. And manipulating N has a nearly magical, transformative effect on the physical reality of data.
So let's trace the journey of increasing N. We already established that with a tiny sample of N equals 20, the histogram drawn from a uniform distribution is an erratic mess.
Yeah, with only 20 pulls of the lever, chance simply has not had enough time to balance its own scales. A purely random cluster of 3 sevens completely distorts the visual landscape of the data.
So as researchers, we scale up our ambition. We increase the sample size from 20 up to N equals 100. At this stage, we theoretically expect each of our 10 numbers to appear about 10 times.
When you look at the histogram for N equals 100, it's still not perfectly flat, but the wild, erratic swings are beginning to encounter resistance.
The tallest bars are dropping, the lowest valleys are filling in.
Exactly. The noise is absolutely still present, but its volume is being turned down.
We push the bounds of our resources further. We expand the sample to N equals 1,000. Now, the expectation is that each number should manifest approximately 100 times.
And the visual transformation here is undeniable. The histogram is aggressively flattening out. The tops of all the bars are hovering incredibly close to the 100 mark on the y-axis. The chaos is losing its grip on the overall shape.
Finally, to witness the ultimate power of volume, imagine we crank the machine up to generate a massive sample of N equal 100,000 observations. We expect each integer to appear roughly 10,000 times.
At N equals 100,000, if you draw multiple separate samples of that massive size, their histograms will look virtually identical to one another.
Because the tops of the bars are aligned almost perfectly at the 10,000 threshold. The true underlying reality of the uniform distribution, that perfectly flat horizontal line, has finally stabilized.
It has overpowered the noise and become visually undeniable.
Now, the mathematical reality is that the noise hasn't ceased to exist. Sampling error is still happening on every single draw.
Right, but proportionally, the noise has been entirely drowned out by the overwhelming mass of the true signal. It's the exact mechanism of flipping a coin.
Oh yeah, explain that.
If you flip a coin just 10 times, landing on 7 heads and 3 tails is not particularly shocking. Chance can easily produce a 7-to-3 ratio.
Sure.
But if you flip that exact same coin 100,000 times, the laws of probability dictate that you are going to land incredibly close to 50,000 heads and 50,000 tails. The true 50-50 nature of the coin reveals itself.
And this progression illustrates a foundational philosophy of statistical thought. Small sample sizes will inevitably display bizarre, extreme, and completely random patterns simply because sampling error holds too much influence over a small dataset.
But as you continuously increase the sample size, the artificial illusions fade, and the true, authentic pattern of the underlying population emerges.
The ability to recognize this stabilization is the essence of inference. Imagine looking at two different histograms, both built from a tiny sample of n equals 20. One is drawn from our flat uniform distribution, the other is drawn from a complex, bell-shaped distribution.
Because n is so small, both graphs just look like a jagged, random mess of bars. You cannot reliably tell them apart.
The sampling error is so loud it acts as a cloaking device.
Exactly. But then imagine looking at two new histograms from those same two distributions, but this time they are built from a massive sample of n equals 1,000.
Suddenly the fog clears. One histogram looks remarkably flat, and the other looks remarkably like a bell curve.
And you, simply by looking at those two stabilized graphs, can immediately point to the flat one and confidently state that data originated from the uniform distribution.
And by making that visual judgment, you are actively performing statistical inference. You've successfully inferred the origin of the data based on the behavioral patterns revealed by a large sample.
And you accomplish this without writing down a single complex formula or calculating a p-value. You simply grasp the core logic of signal versus noise.
It is empowering to realize that inference is intuitive before it is mathematical. But we must take this conceptual intuition and pressure test it against the realities of experimental design.
Yeah, we need to witness exactly how viciously chance can ruin a real experiment if we're not actively guarding against it.
To demonstrate this danger, let's step into a delightfully bizarre, fictitious experimental setup. Imagine yourself as the lead researcher. You are standing in a laboratory, completely blindfolded, standing before a massive, industrial-sized gumball machine.
Okay, I have my blindfold on.
You know for an absolute fact, because you filled the machine yourself, that it contains exactly 50% red gumballs and exactly 50% green gumballs. They are identical in size, shape, weight, and texture. The only variable is color.
Right. And the objective of this experiment is to test a highly specific, admittedly absurd hypothesis. We are investigating whether picking gumballs with your left hand somehow causes you to extract a higher number of green gumballs compared to picking with your right hand.
We are testing for magical color-seeking hands.
We really are.
So let's map our variables. The independent variable, our manipulation, is the physical hand being used. Left condition versus right condition. The dependent variable, our measurement, is the color of the extracted gumball.
Operating entirely blindfolded, you plunge your left hand into the machine, mix them around, and randomly extract exactly 10 gumballs. You place them in a bowl marked left.
You repeat the exact same procedure with your right hand, extracting 10 random gumballs, placing them in a bowl marked right.
The physical phase of the experiment is complete. You remove the blindfold. Now we must confront the expectation versus the reality.
Given that the universe of the machine is a perfect 50-50 split, and given the undeniable biological reality that human hands do not possess specialized nerve endings capable of detecting the color green through tactile sensation alone,
What should the data look like?
well, logic dictates that the left hand should have extracted roughly 5 green and 5 red. The right hand should have also extracted 5 green and 5 red.
But the reality of running this trial yields a different result. You count the inventory. The bowl for the left hand contains 6 green gumballs. The bowl for the right hand contains only 4 green gumballs.
We have a discrepancy. The data points are not identical, 6 versus 4. And this specific moment is where countless amateur researchers step onto a landmine of false inference.
A naive observer, someone who's not internalized the pervasive nature of sampling error, might look at the raw numbers of 6 and 4 and immediately formulate a causal conclusion.
They might declare, the hypothesis is supported. The left hand clearly demonstrates a superior latent capacity for selecting green gumballs.
They write the paper, they publish the findings, they do a TED Talk on the magical properties of left-handedness.
But let's pause and think critically about the mechanics of what just occurred. Why did the left hand acquire 6 while the right hand acquired 4?
We must emphasize this point. The numerical difference is unequivocally, unconditionally not caused by the hand being used.
No, we engineered this hypothetical universe specifically to guarantee that the hands have zero causal power.
The discrepancy of 6 versus 4 is 100% an artifact of sampling error. The mere physical act of dipping a hand into a randomized mixture and extracting a tiny, finite sample of 10 inherently generates minor variations.
It is nothing more than luck. The left hand just happened to close its fingers around a cluster that contained 1 extra green gumball.
But recognizing this is deeply unsettling for the scientific method. We construct massive, expensive experiments entirely to search for differences between groups.
Yeah, and this simple gumball scenario proves that chance, operating completely alone, is capable of manufacturing differences out of thin air that look exactly like legitimate experimental effects.
Chance is the ultimate confounding variable. If random luck can effortlessly generate differences, how can any scientist standing in a real laboratory looking at real data ever know if the difference they discovered is a genuine breakthrough or just a statistical hallucination?
This dilemma brings us to the most vital concept in inference, creating a window of chance. If random sampling error is our primary suspect, we cannot just guess at its capabilities.
We need to drag it into the interrogation room, put it under a microscope, and mathematically map the exact limits of its power. We need to know what chance usually does, and crucially, what chance is utterly incapable of doing.
Fortunately, modern researchers possess a tool to do exactly that: computational simulation. We do not have to guess. We can instruct a computer to simulate that exact gumball experiment, pulling 10 left and 10 right from a 50-50 machine, and we can watch chance operate millions of times in a row.
Let's run the simulation. But instead of keeping track of raw counts of red and green, we need to simplify the outcome into a single, highly useful metric, the difference score.
Right. We're going to calculate the number of green gumballs in the left hand and explicitly subtract the number of green gumballs in the right hand.
The difference score is the ultimate currency of experimental comparison. In our initial trial, the left hand had 6, the right hand had 4. 6 minus 4 yields a difference score of positive 2.
And if the outcome had been reversed, the left hand grabbed 4, the right grabbed 6, 4 minus 6 is negative 2.
And if the universe had been perfectly balanced, 5 in the left, 5 in the right, 5 minus 5 is exactly 0.
So we instruct the computer to simulate this 10 gumball experiment 10 times in a row. We generate 10 different scores. We might see a 0, a positive 1, a negative 2, but 10 trials is far too small a sample to map the true nature of the suspect.
We must escalate. We program the computer to run the blindfolded experiment 100 times. We calculate 100 separate difference scores. We plot these scores on a massive histogram.
And as the graph populates, a profound realization begins to emerge. There are a vast number of bars, indicating that chance is constantly producing differences. However, the horizontal spread of those bars, the actual size of the different scores on the x-axis, appears rigidly constrained.
The graph is populated with differences of 1, 2, maybe 3 or 4. But you scan the outer edges of the graph, and there are absolutely no bars indicating a difference of 8, 9, or 10.
To achieve absolute certainty, we push the simulation to the extreme. We order the computer to run the mock experiment 10,000 consecutive times.
We have just generated 10,000 independent, isolated experiments where we possess godlike knowledge that the only mechanism causing a difference is pure, unadulterated random chance.
I take that massive data set of 10,000 different scores and visualize it as a single histogram.
The resulting geometry of that graph is breathtakingly important. It forms a massive symmetrical bell-shaped curve with its absolute highest peak centered flawlessly at the number 0.
Let's paint a vivid picture of this curve. The highest bar in the dead center is anchored at 0. This signifies that out of 10,000 randomly simulated experiments, the most frequent common outcome by a massive margin was that both hands extracted the exact same number of green gumballs. The difference was 0.
This aligns perfectly with reality. 0 is exactly what champs should produce on average when pulling from a balanced system.
But as your eyes move away from the center 0, stepping outward to +1 and -1, +2 and -2, the bars are still quite tall. Chance is remarkably adept at generating these minor, petty differences constantly.
However, as you continue moving outward toward the extremes of the x-axis to +4, +5, -6, the height of the bars plummets dramatically.
The frequency of these events drops off a cliff, and by the time your eyes reach the numbers 8, 9, or 10, the graph is completely flat. There are no bars.
This beautifully defined bell-shaped histogram is our window of chance. It visually and mathematically defines the strict boundaries of what random variation is capable of manufacturing within the constraints of this specific experimental design.
The window of chance is an interrogation report. It tells us precisely what our suspect usually does, zeros, ones, twos. And more importantly, it provides a hard boundary on what our suspect almost never does, eights, nines, tens.
This leads to the ultimate mechanism of how we actually make scientific inferences. Imagine you step away from the computer simulation, you walk into the physical laboratory, put on the blindfold, and run the gumball experiment for real.
You calculate your actual data, and you find a different score of +2.
You take that real-world result of +2 and you compare it against your simulated window of chance. You look at the graph and you clearly see that chance produces a positive 2,000s of times. It is an incredibly common outcome.
Therefore, you are mathematically forbidden from claiming your left hand possesses magical powers. Your primary suspect, chance, was at the scene, had the motive, and is perfectly capable of having committed the crime of causing that difference.
But consider the alternative reality. You run the physical experiment, you take off the blindfold, and you calculate an astonishing difference score of +9.
You take that +9 and compare it to the window of chance. You look at the outer edges of the histogram, and you see that out of 10,000 simulations, chance literally never produced a +9.
It is statistically virtually impossible for random sampling error to generate that specific result.
In that exhilarating scenario, because you have rigorously proven that chance is an almost impossible explanation, you have earned the statistical right to point your finger at a different cause. You have justification to claim that a real, non-random causal force was at work.
It is the ultimate process of elimination. If you can definitively prove that chance didn't do it, then something else must have. This logic is the beating heart of scientific discovery, and it serves as the perfect foundation for what we can call the Crump test.
I should note that the Crump test is an entirely unofficial framework created by the textbook's author to help build your intuition. You will not find it in a formal glossary of statistical terminology.
But its pedagogical value is immense. It strips away all the terrifying formulas and Greek symbols, relying purely on basic arithmetic adding, subtracting, counting, and graphing to force you to confront the logic of inference.
It reduces statistical decision-making to its absolute bare bones. The framework begins with establishing a frequency-based intuition about risk and occurrence. We can call this the lightning analogy.
Let's explore this. To understand how statisticians make decisions, we must first establish a personal psychological threshold for what constitutes an event that happens a lot versus an event that happens almost never.
Imagine a scenario where meteorologists announce that your specific location has a 1 in 10 chance of being struck by lightning today. Would you go outside and walk to the grocery store?
Absolutely not. A 1 in 10 chance is astronomically high. If I took that risk every day, I would be struck multiple times a month. My threshold dictates that 1 in 10 is happening a lot. I am staying in the basement.
Okay, let us adjust the parameters. What if the stated odds were 1 in 1,000 days?
1 in 1,000 days is roughly getting hit once every 3 years. It is lower, but it is still far too frequent for a fatal event. I am still avoiding the outdoors during storms.
Let's push the boundary further. What if the odds drop to 1 in 100,000 days?
100,000 days equates to over 270 years. At those odds, the risk has evaporated. I am going outside, I am playing golf in a thunderstorm, holding a metal iron in the air, completely ignoring the danger. My brain has categorized that probability as an event that essentially never happens.
Exactly. Every human being naturally possesses an internal cognitive threshold, where a probability crosses an invisible line from a plausible risk I must actively worry about to an anomaly so incredibly rare that I can safely assume it will not occur in my reality.
For the purpose of establishing the rules for the Crump test, we need to arbitrarily select a strict threshold to define the concept of almost never. We will set that boundary at 1 out of 10,000 times.
If chance is only capable of producing a specific numerical result 1 time out of 10,000 attempts, we're going to officially categorize that outcome as almost never. It is rare enough that we are willing to confidently bet our scientific reputations against it.
With our critical threshold firmly established, we can proceed to the second phase, simulating a null experiment. We're going to construct a full, complex psychological experiment inside a computer simulation solely to build a highly customized window of chance.
Let us lay out the parameters. We are measuring a generic construct. Let's call it variable x. We know from vast amounts of historical data that the true population mean for variable x is precisely 100, and the standard deviation is 15.
We design an experiment utilizing two separate groups. Group A will contain 20 subjects and Group B will contain 20 subjects, yielding a total sample size of 40 participants.
Here is the brilliant, counterintuitive genius of this specific simulation. We're going to instruct the computer to run this entire experiment, but we are not going to apply any manipulation whatsoever.
We are going to purposefully, deliberately do absolutely nothing to the groups.
Wait, I need to stop you right there. That makes absolutely no sense. If the entire goal of science is to figure out if an intervention or manipulation actually works, why on earth would we spend time and computational power simulating an experiment where we purposefully ensure that nothing happens? That feels like a massive waste of resources.
It sounds completely backward, almost nihilistic, until you realize what doing nothing actually achieves. By intentionally eliminating any real-world experimental manipulation, we are creating a vacuum. We are isolating the exact, untainted footprint of pure sampling error.
I see the architecture of the trap. Because we are purposefully doing nothing, the only possible logical reason that Group A's average score would differ from Group B's average score is the random dumb luck of which digital participant happened to end up in which group.
Precisely. We are forcing chance onto an empty stage. We are demanding that chance show us exactly what it is capable of doing when it is the absolute only actor permitted to perform.
So the simulation begins. The computer randomly samples 20 numbers from our defined population to form Group A and another 20 random numbers to form Group B. It calculates the mean average for Group A, calculates the mean average for Group B, and then subtracts them to generate a single difference score.
Because both of these groups are being randomly pulled from the exact same underlying population, a population with a known mean of 100, the theoretical difference between their sample means should be 0. 100 minus 100 equals 0.
But because we understand the jagged reality of sampling error, we know the difference will rarely be exactly 0. The computer relentlessly performs this null experiment 10,000 times.
It generates 10,000 distinct different scores produced by absolutely nothing but random chance. It visualizes those 10,000 scores on a histogram.
And once again, the chaos resolves into order. We are presented with a beautiful, symmetrical, bell-shaped window of chance, towering perfectly over the 0 mark.
Now we inspect the outer boundaries of this new map. We look for the extremes. What was the single largest negative difference that chance managed to produce across those 10,000 empty runs?
According to the data, the absolute minimum value scraped the bottom at roughly -22.
We swing our gaze to the opposite side. What was the largest positive difference? The absolute maximum value peaked at roughly +22.
We must ask the critical question. How many times out of 10,000 attempts did random chance manage to spontaneously generate a mean difference of 30?
The answer is 0. Out of 10,000 completely simulated experiments where we purposely did nothing, chance never accidentally produced a mean difference of 30 between the two groups.
We have successfully mapped the absolute, undeniable limits of chance for this highly specific experimental design. We know its geography, which launches us directly into the perilous territory of judgment, decision-making, and errors. This is where we navigate the gray areas of science.
This is the moment we take our newly generated map of chance and begin drawing hard, consequential lines across it. We must define our zones of decision.
Envision that bell-shaped histogram of chance differences. The vast territory stretching from -22 to +22 constitutes our chance could have done it zone. It is the messy, highly probable middle ground.
And everything falling strictly outside of those borders, any different score mathematically greater than +22 or less than -22 is designated as our not chance zone.
Let's apply this map to reality. You leave the simulation, return to the physical world, and run this exact experiment with 40 real human beings in a laboratory. This time you actually apply a revolutionary new therapeutic intervention to Group A, while doing nothing to Group B.
You measure both groups, crunch the numbers, and you discover a stunning mean difference of 25 between the groups.
You immediately consult your map. The number 25 falls entirely, unequivocally, within the not chance zone.
Because your simulation proved that chance produced a difference of 25 exactly 0 times out of 10,000 attempts, you possess the statistical armor to confidently reject chance as a plausible explanation.
You can celebrate, draft your paper, and state, the data indicates my therapeutic intervention actually worked.
But the real world is rarely that generous. What if you run your physical experiment, exhaust your grant money, and your final result yields a difference of exactly 10?
10 lands squarely in the deepest, thickest part of the chance could have done it zone. Your simulation shows that chance manufactures differences of 10 constantly, without breaking a sweat.
Confronted with that reality, you have to sigh in frustration and admit defeat. You must say, well, my therapeutic intervention might have had some subtle effect, but chance is an incredibly plausible suspect. I cannot rule it out. I cannot claim victory.
But science is not always a stark binary of obvious success or obvious failure. We must introduce the truly agonizing aspect of behavioral science, the reddish-gray areas.
Let us imagine the most frustrating scenario. You run your real experiment and the data yields a difference score of 15.
15 is technically located inside the boundaries of the chance window, yet mathematically less than our absolute maximum limit of 22. The simulation proves that chance did occasionally produce differences of 15.
But it didn't do it very often. A score of 15 is located way out on the tapering edges, the thin tails of the histogram. It is a rare occurrence.
This specific coordinate is where rigid math ends and human judgment begins. You are holding a different score that chance is capable of producing but rarely does. You face an agonizing choice.
Do you place your bet that this specific outcome was just a bizarre, rare fluke of chance? Or do you bet that your manipulation actually caused it, overriding the unlikeliness?
You will never escape the uncertainty in this zone. Brilliant, highly reasonable statisticians will aggressively disagree on exactly where to draw the definitive line in these gray areas.
And precisely how you choose to draw those lines. Your personal philosophy of risk dictates the types of catastrophic errors you are destined to make over the course of your scientific career.
The architecture of Inference breaks the cost of our decisions into two distinct categories, Type I and Type II errors.
These errors are the occupational hazards of the scientific method. Let us define them with absolute clarity. A Type I error is classified as a false positive.
I always conceptualize a Type I error as the scientific equivalent of the boy who cried wolf. You run your experiment, you observe a different score in your data, and you excitedly rush to publish a paper boldly declaring, I have found a real, meaningful effect.
But the devastating reality is that you were completely fooled. The universe tricked you. It was merely a weird, incredibly lucky fluctuation of chance that happened to perfectly mimic the signature of a real effect.
You confidently called a finding real, when it was, in fact, nothing more than random noise.
The opposing trap is the Type II error, officially known as a false negative.
A Type II error is the tragedy of missing the forest for the trees. You run your complex experiment, you observe a different score, perhaps it lands right in that agonizing reddish-gray area.
You decide to play it safe, protect your reputation, and you declare, that's probably just random chance. I cannot confidently claim the effect is real.
But the invisible reality is that your manipulation was actually working. It was genuinely changing the world, but it produced a signal that was just weak enough to get confused with the ambient noise of chance.
You tragically ignored and abandoned a real, valid scientific discovery because you incorrectly blamed the outcome on chance.
There is an inescapable, cruel trade-off baked into the physics of these errors. If you adopt a philosophy of extreme caution setting, incredibly strict, uncompromising rules that dictate the stack, you will only ever believe an effect is real if it lands deep, deep into the not chance zone. You will successfully protect yourself.
You will almost never make a Type I error. You will never be the researcher who cries wolf.
But the price of that extreme strictness is that you will inevitably commit a massive volume of Type II errors. You will miss dozens of subtle, real, potentially world-changing discoveries because you are constantly tossing every ambiguous result into the chance garbage bin out of fear.
Conversely, if you operate with a highly liberal philosophy, enthusiastically accepting anything that lands even remotely in the gray area as a real publishable effect, You will be a pioneer.
You won't miss many real discoveries, minimizing your type 2 errors. But your career will be littered with false positives. You will publish a mountain of type I errors, polluting the scientific literature with claims that cannot be replicated.
It is a terrifying balancing act, and I want to pause here to ring a massive alarm bell for a critical misconception alert.
Let's hear it.
When an experimental result falls squarely inside the chance window, and a researcher states that the finding is not statistically significant, or they conclude that they cannot rule out chance, observers often violently misinterpret that statement.
They assume it is definitive proof that the manipulation absolutely does not work.
That is perhaps the most pervasive and dangerous error in scientific literacy. Landing inside the chance window does not in any way prove that your experimental manipulation was a failure. It is simply an admission of ignorance.
It means your data contains far too much static, too much uncertainty, to be able to cleanly separate your manipulation's potential signal from the random noise of the universe. The effect might absolutely be there, functioning perfectly, but it is buried too deeply in the mud to see clearly.
There is an alternative philosophical approach to navigating this maddening uncertainty, an approach known as Bayesian statistics.
Traditional frequentist statistics often forces us into a corner where we must draw strict binary lines in the sand, significant or not significant, the green zone or the red zone.
Bayesians reject that binary. They prefer to operate in infinite shades of gray, or, to use a visual from our previous examples, shades of blue.
Imagine our histogram of chance differences, but instead of being a solid color, the bars are painted in a gradient. The bars clustered around zero are a very pale, washed-out light blue.
This faint color represents an extremely low level of confidence that any observed effect is real. But as the different scores grow larger, moving outward, the bars transition into a deeper, stronger, more resolute dark blue, representing a steadily increasing level of confidence.
Instead of demanding a strict artificial cutoff point to make a definitive yes or no decision on a single, isolated experiment, the Bayesian framework deals in the gradual, continuous shifting of confidence.
You approach an experiment with prior beliefs, you observe the data, and you smoothly update your level of confidence based on the weight of that new evidence. It is a more fluid, perhaps more organic philosophy for handling the inescapable reality of uncertainty.
But regardless of whether you pledge allegiance to the Bayesian or the traditionalist camp, you are still forced to grapple with the brutal reality of hunting for weak signals in a violently noisy world. Which brings us to the concept of designing a better experiment, or, as it is playfully known, the power of grayskull.
This section confronts a massive, depressing dilemma that haunts researchers: the agonizing problem of genuinely weak manipulations.
Let us construct the dilemma. What if your experimental manipulation is entirely real, it genuinely works exactly as you theorized, but the magnitude of its effect is just inherently, fundamentally weak? Consider the hypothesis that listening to classical music while studying boosts statistics exam scores.
It is a highly plausible, widely debated hypothesis.
But let's be realistic about the human brain. Listening to Mozart is not going to magically transform a failing student into a brilliant mathematician. Realistically, the music might only boost a student's final score by a mere 5 points. It is a real effect, but a tiny one.
We must recall the ruthless math of our previous null simulation. In a standard, moderately sized experiment utilizing 20 people per group, chance routinely, effortlessly produced wild swings of 10 or 15 points in either direction without any provocation.
That is the tragedy. If the actual real-world effect of your music intervention is only positive 5 points, but the ambient background noise of chance is regularly throwing around positive 10s and negative 15s, your tiny, fragile, real effect is going to be instantaneously swallowed whole by the noise.
A difference of 5 will always permanently reside deep inside the chance window. You will run the experiment perfectly, the music will actually work, and you will never, ever be able to confidently claim victory.
So, confronted with this physics problem, what is the recourse? Do researchers simply abandon the pursuit of subtle, nuanced phenomena? Do we only study things that hit subjects like a sledgehammer?
Absolutely not. And this is the moment we reveal the true superpower available to the researcher. The solution lies in the architecture of experiment design, specifically the power of intentionally altering your sample size.
We discussed earlier how increasing the sample size n helps stabilize a simple descriptive sample, allowing the true distribution to emerge from the static. But in the specialized context of different scores and experimental comparison, Increasing n accomplishes something vastly more profound.
It literally alters the physical geometry of the chance window itself.
The visual mechanics of this are breathtaking. We return to our computer and run our null simulation, doing absolutely nothing but watching chance create random difference scores between two empty groups. But this time, we run the entire massive simulation 4 separate times, aggressively doubling the sample size for each new run.
We execute the first simulation with a tiny n equals 20 per group. Then we expand to n equals 40, then n equals 80, and finally a robust n equals 160 per group.
As the value of n escalates, the sampling distribution of the mean differences. The physical width of our window of chance begins to shrink dramatically. It looks as though an invisible vice is squeezing the histogram from both sides, collapsing the entire structure inward toward zero.
Let us examine the precise limits. When the simulation utilized an n of 20, we saw that the absolute largest difference chance could randomly produce was hovering around 22 points.
A 22-point spread creates an incredibly wide, forgiving window for chance to operate within.
But observe what happens when we double the sample to an n of 40. The window compresses. The absolute largest difference chance managed to produce across 10,000 runs drops to only about 16 points.
We double it again to an n of 80. The vice tightens further. The maximum power of chance is crippled, maxing out at a difference of roughly 14.
And when we reach our massive, highly powered design of n equals 160, the largest difference chance ever produced in the entire simulation collapsed all the way down to a mere 12 points.
This mechanism is nothing short of incredible. By simply recruiting more human participants, by increasing the sheer volume of data, you are actively neutralizing the wild, erratic swings of chance.
You're not just measuring the world better, you are literally building a tighter, sharper, more precise scientific instrument.
This phenomenon directly solves our agonizing dilemma of the weak manipulation. If your classical music intervention truly only causes a tiny 11-point boost in test scores, an experiment poorly designed with an n of 20 will never ever reliably detect it.
Why? Because in an n of 20 universe, chance effortlessly produces 11s all the time. Your real signal is entirely camouflaged by fake signals.
But if you invest the time and money to run that exact same music experiment with a massive sample of n equals 160 subjects, the geometry of the chance window has shrunk so severely that chance never reaches at 11. It tops out at 12.
Therefore, if you observe an 11-point difference in your massive n equals 160 experiment, you possess the rigorous mathematical authority to point directly at the classical music and state, chance is mathematically incapable of doing this in a sample this large. The music unequivocally worked.
This vital concept, the mathematical ability of a specific experimental design to successfully reliably detect a true effect without it getting lost in the noise, is what statisticians refer to as statistical power.
Power is the ultimate measure of the sensitivity of your design. It is the resolution of your microscope.
It perfectly justifies the joke. By the power of Grayskull, I have the power. When you engineer an experiment with a massive sample size, you literally possess the power to conquer random chance. You have the power to confidently, unequivocally state that chance did not ruin your life's work.
The visual representation of power is striking. If you chart the maximum and minimum boundaries of chance differences across a sliding scale of sample sizes, from a tiny n of 10 all the way to a massive n of 300, the resulting graph looks exactly like a funnel violently tapering inward as it moves to the right.
If you are hunting for a specific effect size, say, you need to prove a difference of exactly 10 points. You simply draw a horizontal line straight across a graph at positive 10 and negative 10. You can visually pinpoint the exact moment the tapering funnel of chance drops permanently below your target lines.
The graph reveals that experimental designs utilizing an n of 100 or greater almost never produce chance differences of 10. Therefore, if you are searching for a 10-point effect, an n of 100 design is highly sensitive, highly powered, and perfectly calibrated to detect that reality.
It ultimately comes down to strategic planning. If you are venturing out to hunt for a tiny, subtle effect, you cannot use a small net. The holes are too big. The effect will slip through. You need to weave a massive, dense net of data.
That comprehensive understanding wraps up the intuitive, formula-free logic of the Crump test. We have built the philosophical foundation. Now we are ready to transition into the rigorous application of these ideas with the randomization test.
Also known in some circles as the permutation test. This is a monumental threshold. We are moving from intuition to the first official inferential statistic.
Everything we have discussed thus far was designed strictly to build your conceptual muscles. Now, we take those exact same philosophical tools, the simulation of chance, the construction of a chance window, the isolation of sampling error, and we apply them to a formal, rigorous statistical procedure.
The profound elegance of the randomization test hinges entirely on a beautiful, direct contrast. It forcefully compares what actually did happen in a physical experiment against a simulated universe of what could have happened purely by chance.
To illustrate the mechanics of this test, let's establish a hypothetical experiment that strikes at the heart of student anxieties. Does the physical act of chewing gum during a statistics exam actually improve your final grade?
A question of vital importance. Here is the architecture of the setup. We recruit a total of 40 statistics students. We utilize strict random assignment to place 20 students into the active chewing gum condition and the remaining 20 into the sterile no-gum condition. They sit down, they take the grueling exam.
We collect the exams, grade them, and analyze the data. We sum the individual scores and calculate the mean average for both groups. The data reveals that the mean score for the 20 students who actively chewed gum during the test is 80.65.
A highly respectable B-.
We then calculate the mean score for the 20 students restricted to the no-gum condition. Their average is a bleak 65.65.
A solid D. The contrast is stark. We calculate the observed mean difference by subtracting the two. 80.65 minus 65.65 yields a massive, undeniable difference of exactly 15 points.
The students who chewed gum scored a full 15 points higher on average than those who did not.
If I am the lead researcher on this project, I am absolutely thrilled. I am calling a press conference, I am contacting gum manufacturers for sponsorships, I'm declaring that chewing gum is the ultimate cognitive enhancer for mathematics.
But as a statistician, it is my professional duty to step in and play the role of the aggressive, cynical skeptic. I look at your glowing 15-point difference and I say, look, I acknowledge that you utilized random assignment, but chance is an incredibly tricky, malicious force. Consider this highly plausible alternative reality. What if, purely by the blind luck of the draw, the 20 smartest, most mathematically gifted students in the entire class all accidentally ended up in the gum group?
That is a deeply annoying argument because I have to admit it is physically possible.
And let us assume, the skeptic continues, that the 20 students who struggle the most with numbers all tragically ended up assigned to the no-gum group. In that specific scenario, the physical act of chewing gum did absolutely nothing to their brains. The 15-point difference is entirely 100% an artifact of the random assignment accidentally stacking the deck.
As the researcher, how do I possibly defeat that argument? I cannot rewind time and rerun the physical experiment with those exact same humans 1,000 times to prove it wasn't a fluke of assignment.
No, you cannot rewind reality, but you can simulate alternate realities within a computer. You can simulate the universe. And this mechanism is exactly how the randomization test operates. We are going to directly, mathematically test the skeptic's exact premise. What if the gum was entirely useless and the scores simply belonged to the innate intelligence of the students, regardless of which group they were forced into?
We need to walk through the mechanics of this test with absolute precision because it is brilliant. We take all 40 of the graded test scores, we completely strip away the experimental labels of gum and no gum, we erase the groups, we are left with just a single, undifferentiated pile of 40 numbers.
And then we play God. We shuffle the universe. We take that single pile of 40 scores, we randomize them completely, and we deal them back out into two brand new, entirely artificial piles of 20. We've created a new, completely randomized Group A and Group B.
We then act as if this was real data. We calculate the mean average of this new fake Group A, calculate the mean of the new fake Group B, and we find the difference score between them.
That singular action constitutes one randomization. It represents one mathematical example of what could have happened to the group averages if the assignment of students was dictated by nothing but pure, unadulterated random luck.
To make this process incredibly concrete, let's describe a visual animation that beautifully illustrates what the math is doing behind the scenes. Imagine a digital graph with two distinct vertical columns, condition 1 and condition 2.
At the beginning of the animation, you see a cluster of individual green dots resting in condition 1, representing the actual test scores of the real subjects in the gum group. In condition 2, there is a cluster of red dots representing the real scores of the no-gum group.
Hovering above each cluster is a large, solid purple dot. That purple dot represents the actual real-world mean average for that specific group. The vertical distance between those two purple dots represents our original observed difference of 15 points.
Now we trigger the randomization animation. Suddenly, the individual green and red dots detach from their columns and begin violently flying back and forth across the screen, scrambling themselves into endless, completely random combinations of two groups of 20.
As the dots frantically shuffle and reorganize, new, bright yellow dots flash onto the screen. These yellow dots are calculating the new, randomized mean average for each fake group every single time the deck is reshuffled. You watch these yellow dots bouncing erratically up and down as the data is continuously reorganized.
You focus your attention on the range of motion of those bouncing yellow dots. They are drawing a visual map of exactly what kind of mean differences random shuffling pure chance is capable of producing with these specific 40 test scores.
In this specific animation, the yellow dots bounce around quite a bit, exploring the middle of the graph. But you notice something crucial. They never, ever bounce high enough or low enough to reach the position of the original solid purple dots. The 15-point gap of our original difference lies entirely outside the chaotic, bouncing range of the random shuffles.
It is a stunning, irrefutable visual form of statistical inference. You can literally watch chance exhaust itself, visually proving that it is fundamentally incapable of reaching the reality represented by the purple dots.
So we take this beautiful visual logic and apply it back to the cold math of our chewing gum experiment. We instruct our computer to shuffle those 40 real exam scores not just once, but 1,000 separate times. We instruct it to calculate 1,000 entirely random mean difference scores.
And we plot those 1,000 fake difference scores into a histogram.
We have just successfully built a custom-made window of chance that is precisely calibrated to our exact specific data set. It reveals every possible mean difference that random assignment could have accidentally produced if the chewing gum was completely inert.
As we have come to expect, the center of this new histogram is anchored firmly at 0. It spreads out, creating a bell shape into the positive and negative numbers.
And now we arrive at the moment of absolute truth. We take our observed difference, the 15-point victory we found in the physical reality of the classroom. We take a bright blue marker, and we draw a solid vertical line on the graph's x-axis exactly at the number 15.
Where does that blue line fall in the landscape of the graph?
It is located incredibly far to the right. It exists completely, entirely outside the bounds of the histogram. The histogram representing the power of chance differences tapers off in flat lines somewhere around 10 or 12. It doesn't even come close to touching our blue line of 15.
So we stand before the skeptic. We compare what actually did happen in reality, the blue line standing alone at 15, against the entirety of what could have happened by chance, the isolated bell curve. The reality of what happened simply does not exist within the mathematical universe of what chance is capable of doing.
The skeptic is utterly defeated. We can look them in the eye and confidently state, chance did not do this. It is mathematically impossible for random assignment to have produced a 15-point difference with these specific test scores. Therefore, we possess rigorous statistical confidence that the chewing gum actually exerted a real, measurable effect on cognitive performance.
But to ensure we remain intellectually honest, we must explore a counterexample. What if, when we ran the original physical experiment, the observed difference between the groups was only a meager 5 points instead of 15?
If the reality was only a 5-point difference and we took a red marker to draw a vertical line at the number 5 on the x-axis, that red line would stab directly into the thickest, tallest part of our randomized histogram.
It would be swallowed whole by the chance window. In that devastating scenario, the skeptic is victorious. We would be forced to concede that a difference of 5 points happens constantly just by randomly shuffling the smartest students between groups. We would have zero mathematical authority to conclude that the gum did anything at all.
And that, beautifully and simply, is the architecture of the randomization test. It is stunningly elegant. It bypasses abstract theoretical probabilities by using your actual, physical data to build a highly customized window of chance. It answers the fundamental existential question of inference without ever forcing you to memorize a massive, impenetrable equation.
It is the absolute perfect distillation of the underlying logic of inference. It makes the invisible math visible.
Which brings us to our conclusion, a moment to step back and recap this incredible paradigm-shifting journey through the foundations of inference.
We have covered a vast expanse of conceptual territory, but every single concept revolves around one singular, unyielding axis, the rigorous resolution of uncertainty.
We began this deep dive with a seemingly simple question. When you observe a difference in your experimental data, how do you know if it is real? The profound answer we have uncovered is that inferential statistics is entirely dedicated to answering the deeper question, where exactly did my data come from?
We discovered that chance, the natural variance of the world, the inescapable reality of sampling error, is always a prime suspect. It is a chaotic force perfectly capable of manufacturing differences out of thin air, simply through the mechanical act of taking a limited sample, as we proved with the blindfolded gumball experiment.
To combat the chaos of chance, we learned how to play God and simulate the universe. Whether utilizing the intuitive foundational logic of the Crump test or deploying the formal, rigorous machinery of the randomization test, we learned how to construct a window of chance, a definitive mathematical map defining precisely what random noise can and cannot accomplish.
By meticulously comparing our actual hard-won experimental results against that theoretical window of chance, we deploy a system of logical deduction to determine whether our scientific manipulations are actively changing reality or if we are merely being hallucinated by the natural variance of the cosmos.
We explored the critical, physics-altering importance of sample size, the mighty letter N. We witness how massively increasing our N literally crushes the chance window, granting us the statistical power necessary to detect real, subtle, fragile effects without tragically abandoning them to type 2 errors.
We navigated the agonizing reddish-gray areas of scientific decision-making. We dissected the painful trade-offs between committing type I false positives crying wolf and type 2 false negatives missing the cure. And we briefly touched upon the nuanced philosophy of Bayesian confidence as an alternative to rigid binary thinking.
It represents a complete foundational paradigm shift. You are no longer merely describing static data, you are actively interrogating the universe. And as we prepare to sign off, I want to leave you with the final, slightly provocative thought to carry with you beyond the classroom.
I believe the best science always leaves you with a lingering question about your own reality.
This entire deep dive has been dedicated to demonstrating with mathematical certainty that chance is constantly, relentlessly producing patterns in small samples that look incredibly real but are entirely fake. Our human brains evolved as desperate pattern-seeking machines. We are biologically hardwired to look at a random difference of 6 versus 4 gumballs and instantly invent a magical causal narrative to explain it.
We are hyperactive narrative machines navigating an intensely noisy random world.
So consider this. If chance is powerful enough to entirely corrupt a strictly controlled, perfectly designed laboratory experiment, how many massive, life-altering conclusions do you jump to in your everyday life based purely on the infinitesimally small sample sizes of your own personal experience?
The implications of that are staggering.
How often do you interact with 2 rude individuals from a specific city and instantly infer a rigid, prejudiced rule about the entire population of that city? How often do you experiment with a new diet for a mere 3 days, observe a tiny random fluctuation on the bathroom scale, and excitedly declare you have discovered a miracle cure?
We commit these errors constantly. We walk through our lives generating massive, consequential type I errors on a daily basis, simply because we lack a mathematical window of chance to contextualize our daily experiences.
The realization is humbling. Statistical inference is not merely a dry academic tool reserved for behavioral scientists in white coats. It is a profound lens for critical thinking. It serves as a relentless reminder to remain intellectually humble about what we think we know to be true, and to always pause and ask ourselves, could chance have done this?
It is the ultimate mathematical argument for intellectual humility.
It truly is. Now, as we bring this mission to a close, I must remind you that while this deep dive was meticulously designed to build your conceptual foundation, to make the intimidating logic of inference feel intuitive and grounded, it remains exactly that, a learning companion.
Understanding the philosophy does not exempt you from doing the mechanical work.
This audio experience is absolutely not a replacement for doing the hard work. You must return to your course materials, read the chapter, engage with the text, boot up the software, run the ARC code simulations yourself, and grind through the practice problems until the logic becomes second nature. You possess the conceptual map now. It is your responsibility to go out and physically explore the territory.
The muddy waters of behavioral science are significantly less terrifying when you possess a fundamental understanding of how the invisible currents operate beneath the surface.
And we genuinely hope we have helped illuminate some of those currents today. We may never possess a clean, simple, binary X-ray machine for the complexities of the human mind, but with the rigorous logic of inferential statistics, we possess something arguably more powerful. We have a mathematically precise flashlight.
A flashlight that cuts straight through the noise.
Keep shining that light, never stop asking the difficult questions, and we will see you on the next deep dive.